So, the nervous system, there's two. Um, the nervous system is broken down into the central nervous system and the peripheral nervous system. And the central nervous system consists of the brain and the spinal cord, whereas the peripheral nervous system are all the nerves that then come out from the brain and from the spinal cord to your extremities and to the periphery of your body. And we can further divide the peripheral nervous system into the afferent or the sensory division, and that's the division that brings information back to the central nervous system. So it might be giving information about pain and sensations. It can give information from our muscles, how our muscles are contracting and things like that. And then the efferent division, or the motor division, sends impulse or information out to our periphery. And that is further divided into the somatic nervous system. And those are primarily the motor nerves that we talk about that stimulate the skeletal muscles to contract. It's more voluntary. And then the autonomic nervous system is more involuntary type of control. So when you change position to maintain your blood pressure, maybe your smooth muscle surrounding your arteries constricts or dilates. So it's something autonomic or automatic. And that is further divided into the sympathetic and the parasympathetic. And the sympathetic is generally types of things that stimulate our nervous system. Our heart beats faster. It slows down digestive activity. It's that fight or flight mechanism to prepare your body for action. And then the parasympathetic nervous system is more what slows down your heart rate. And this is the time when your body restores itself and you have increased digestion. So when we look at a neuron, there's the cell body. We have dendrites that come off the cell body that pick up impulses from other nerves. And then the impulse or action potential is transmitted down the axon. It's insulated with this myelin sheath, which insulates it so that the impulse does not go to other neurons. And you can see where there's the terminal axon where it then innervates muscle fibers. And we have the neuromuscular junctions where the axon makes contact or is in close proximity with the motor end plate. And so motor units, we can talk about the motor units can be, very small motor units, or they can consist of innervation to many muscle fibers. And so we can talk about small or large motor units. But either way, there's what's called an all or none principle. And that means is if that nerve is stimulated and initiates an action potential, all of the muscle fibers that are innervated by that nerve will all respond. So you can see how large motor units with this all or none principle, if it's stimulated, it will have a strong contraction compared to a small motor unit, which will have create less force because it does not innervate as many muscle fibers. And each of the motor units has a threshold. So when we see smaller motor units, they have a lower threshold to be stimulated, and large motor units have a high threshold for stimulation. And there's a recruitment where to produce a muscle force, usually the slow twitch or the small motor units are recruited first, and then the threshold as the stimulus increases, it has to be a stronger stimulus to meet the threshold to recruit those larger motor units. And so we have our slow twitch being recruited first because they have a lower threshold and they're a smaller motor unit. And eventually, as we keep recruiting more and more motor units, we'll eventually get to the fast twitch, the type 2X fast twitch. that are larger motor units, and they will create, they need a greater stimulus to meet the threshold to stimulate the nerve, and they will have a greater force production. And so this is just looks at two motor neurons where you can see motor neuron A is a smaller motor unit compared to motor neuron B, which innervates more muscle fibers. And the size principle, just as I said before, smaller motor units are recruited before the larger units. Those smaller units, as we said before, are slower contracting and tend to be more fatigue resistant. So that's just pretty much what I just said. Larger stimulus needed to recruit the fast twitch, and so those larger motor units will create more force. Now, there's some other things that will determine the force of contraction. One is what's called recruitment, which is what we talked about, is as we keep increasing the motor units and the threshold, we're going to have a stronger contraction. Slow twitch muscles oftentimes will do what's called an asynchronous recruitment, where they'll stimulate one motor unit and then another motor unit, and the other one will relax, and so that's why there's not this fatigue factor. But with fast twitch fibers, we don't have this asynchronous where we have different groups resting. It's a large unit and the whole thing contracts, and so that is prone to more fatigue. And rate coding has to do with how the frequency of the impulses traveling down the axon to create the action potential. So there's something called summation, meaning that if you have a nerve that or a motor unit that is stimulated, it stimulates the muscle to contract, it contracts and relaxes. But if we keep sending these impulses down, it will have contraction relaxation phases more frequently. And so if we have a shorter interval between the impulses, many times it doesn't allow a full relaxation, and we keep having contraction after contraction. And so the faster they come, it's a summation of those forces, and so rate coding, or the frequency of impulse, can result in a stronger muscle contraction. Max force production is what's called specific tension, and that just looks at how much force can be produced per unit area. And so this is going to be greater with fast twitch fibers because they are larger fibers. And fiber efficiency just looks at how much force can be produced with a given amount of ATP. All right, so we talked about sensory information coming back to the central nervous system. And we have these mechanisms within the muscle that send information back to the nervous system when we have muscle contractions or stretching. And there's these fibers that lay within the belly of the muscle called muscle spindles. And they lay parallel to the muscle fiber. And they will sense when the muscle is being stretched. And if the muscle has a strong stretch, they will have a responding contraction to shorten the muscle when they sense a great stretch. And we also have these other protective mechanisms within what are called Golgi tendon organs, and those are where the muscle meets the tendon. And the Golgi tendon organ senses the degree of contraction. So when there's a strong contraction, the Golgi tendon organ will stimulate the muscle to relax, and it's a protective mechanism because it's trying to protect too great a force from causing injury at the site where the tendon attaches to the bone. So we have these, the muscle spindle within the muscle prevents overstretching of the muscle, and it has this muscle contraction which we call a myostatic or stretch reflex. And so this can also be used in sports in a beneficial way with plyometric training, where we do a stretch, put the muscle on stretch, and then there's this responsive muscle contraction. Golgi tendon organs, we also use this in what are called PNF stretching, which results in relaxing the muscle. And so we can sometimes get a greater stretch with that as well when we put a little, have a contraction followed by the relaxation.